Here, so let's go ahead and get started. Thanks again for joining us today. My name is Kevin Hill, and I lead up marketing here at Kaleido. Today we have a great session. We have one of our co-founders and head of protocol, Zhang, with us. Jim's been innovating in enterprise blockchain really since it began, and lately he's been leading the way on developing solutions for privacy and blockchain-based systems. For today's webinar, Jim's going to dive into one of those solutions. I'll give you an overview of how to build with UTXO and zero-knowledge proofs. And then he's going to demo a number of privacy patterns that leverage those. So it's going to be a great session. We're excited to have him with us today and excited to have all of you with us. Just a few pieces of housekeeping before we jump into it. This is being live streamed on LinkedIn and it's also being recorded. So we'll send that recording out after the webinar along with Jim's slides. If you have any questions as you go, feel free to drop them in the chat and we'll answer what we can as we go along. We'll also save some time for Q&A at the end. That is all I have. So, thanks again for joining today. And with that, I'll turn it over to Jim.
All right. Thanks, Kevin. So can you guys see the slides?
Yep, looking good.
Okay, awesome. So hey, everyone, I'm Jim. So this is the second of the series to focus on privacy on blockchain, especially in particular for enterprise use cases. For those who didn't attend the first session, I'll do a 3-slide to do a overview, a summary of what we talked about in terms of privacy techniques within the enterprise blockchain space. So we see the privacy approaches in 3 categories. From left to right, it goes from well-practiced, well-understood to more novel, more leading edge. So on the very left end, we have the boundary security. This is essentially what we've been doing in the quote-unquote Web 2 space, using OAuth security, user authentications, API security. So this is protecting access to the chain with user authentication. And other techniques in this category also includes isolating data, such as when we use Hyperledger Fabric channels, or if we use permission Besu chains and there are different chains, then accessing the ledger will require permission. So that's pretty well understood. On the other hand, if we want all the participants to join the same chain and there is security for the data that are shared, then it gets a bit more involved. So now we come to the second category. Using a split between on-chain state and off-chain state, this was pioneered by the JP Morgan team when they designed the Tessera or Constellation pattern for private transactions. So there are private states that each party and their counterparties in the transaction can maintain. But there is a hash that gets sent to the shared ledger. So all the parties in the Ethereum network will have a hash that represents the private transaction, but the actual transaction payload is hidden from all the parties except for the counterparties within the transaction. Similar idea was also used in R3 Corda, as well as Canton demo architecture, where states are only maintained by the parties that are involved in the transaction. For any parties in the network that are not part of a transaction counterparty, they don't even have the state. So that's going a bit further in terms of maintaining private states. And then we come to the right-hand side with zero-knowledge proof and other advanced cryptographies, where on the shared global ledger, we have a shared state, but the state are designed in such a way that unless you have the necessary private keys, you won't be able to know what the private states are. And smart contracts are convinced that those transactions that include private states are still honest transactions through zero-knowledge proof. Zero-knowledge proof is the technology itself is not the focus of today. At a high level, it's a way to convince someone that a bunch of computation was done honestly with both public inputs that are known to the verifiers, but also private inputs that are hidden from the verifiers. But in the end, the verifiers can be convinced that the computation was done correctly according to a certain spec. So our focus for today is going to be in the right-hand side to focus on how to apply zero-knowledge proofs to apply privacy to a shared global ledger. For example, tokens are a very useful construct. To do a token-based use case solution, you necessarily have to maintain a global state. So in terms of the overall token supply, and for every transaction, there's no tokens that are lost and no value is being created from thin air. All that needs to involve zero-knowledge proof, and we'll see how that is done very shortly. Second slide I'd like to go through as part of the summary is if we look at what are the available solutions when we talk about privacy with zero-knowledge proof. First, we see there are layer one blockchains such as Zcash, which is really sort of the pioneer in this space to apply zero-knowledge proof for privacy. It's a UTXO-based architecture. It doesn't have any smart contract capabilities. So Zcash is similar to Bitcoin, which is just for exchanging value, but in the privacy preserving manner. And then for layer two blockchains, Aztec, which is a layer two under Ethereum, has privacy built in. It's also a UTXO-based design, and it's Ethereum layer two in particular. Some of you may be wondering, what about the other zero-knowledge proof-based layer twos? There's a whole bunch of them. ZK Sync, loop rings, the new ZK EVM-based such as Linea, Polygon ZK EVMs, and so on and so forth. What about those? Don't they have privacy? So the answer is no, they don't have privacy because even though they use zero-knowledge proof to represent their state between layer two and layer one, in order to properly validate the proofs that are uploaded to layer one, you have to provide all the transaction states or the transaction inputs to layer one, which means at that point, all the transactions are going to be public knowledge. So that even though zero-knowledge proof is used in those layer two designs, privacy is not part of those architecture. But Aztec itself has encrypted states, so privacy is built in. A third category of privacy approaches with zero-knowledge proof is privacy token implementations. So these are different from the other two in that they are implemented on standard EVM protocol. It doesn't require the designs and enhancements at the protocol level. You can deploy these tokens such as anonymous Ether to any EVM-based blockchain. And then we come to the second category of ZKP approach, which is I'm going to design my own ZKP circuits. And this is the focus of today's session. In terms of the toolkit and ecosystems, we have a couple available to us. Circom and Socrates are pretty mature systems. They have been used for a couple years by now by multiple project teams. Aztec Noir is a new DSL language that allows you to design ZKP circuits. It's developed by the Aztec Layer 2 team. And finally, Starlight is a language that's mostly based on Solidity syntax itself, with a few keywords that you can add to express what states needs to be kept hidden and which ones are public knowledge. So a third slide I'd like to share is at a high level, when you design a token system, you have two architecture choices, either UTXO or account model. So the difference between the two is for on-chain states with the UTXO design, every value is represented as a separate independent state, whereas in the account model, you have account and balances. So every piece of state is a aggregated account value that belongs to an account. And in terms of the on-chain state cryptography with UTXO, each UTXO is using commitments rather than values in order to hide the value for privacy purposes. But if you use an account model, then your commitments, or you can also use encryption, must be additively homomorphic, which means we are adding the ciphertext either from the commitment hashes or from the encryption scheme to add them together so that at the end, you still have a one value for the account to represent the balance. The transactions with a UTXO design usually includes a array of input UTXOs, which will be spent by that transaction, and an array of output UTXOs, which will be generated by that transaction as new values. With the account model, the transactions will update the sender's account balance by decrementing it, and update the receiver's balance by incrementing it. And of course, in our case with privacy, the updates will be on the ciphertext rather than the clear value. There are implications to concurrency when you make the choices between the two. With UTXO, you get better concurrency because every UTXO is independent from the other. Whereas if you use an account model, and we've seen this with anonymous Zither in our last session, updating a account balance requires careful coordination because a zero-knowledge proof that's part of the transaction payload must be generated based on the latest balance that the smart contract will be using to validate the zero-knowledge proof. So careful coordination must be used between the off-chain client that's generating the proof versus the smart contract, which is maintaining the latest balance. And there's some balances we have to make between doing that versus allowing the zero-knowledge proof to be generated correctly. And finally, in terms of building applications with these architectures, a UTXO model client is quite a bit more complex because you must index all transactions that's happening on the chain. Otherwise, you could be missing part of your balance because you missed some incoming UTXOs from applications that you missed indexing. So to figure out your balance, you need to index all the transactions that has happened on that chain up to this point and add them together. That's how you can figure out your balance. Whereas with account model, it's quite simple. You ask the smart contract, what is my current balance? And you get the ciphertext from the on-chain query, and then you decipher from that to recover your balance. So the client for account model can be quite simpler. So now let's look at what exactly does it take to design a confidential UTXO toolkit that allows us to use the UTXO model with privacy and with a spectrum of choices. So at the high level, the constructs we need to use to design such a system, as we mentioned, instead of clear text values on chain, we need to hide them. And the way to hide them is to use commitments or hashes. And then when we construct a transaction, the input UTXOs will be a list of commitments to be spent. We will see later that some patterns allow us to have anonymity, which means we're hiding which input UTXOs are being spent, and we're hiding the ownership of each UTXO. So instead of specifying which UTXOs are being spent, we're specifying a secret that we call nullifiers that are securely bound to the UTXOs that are being spent. But looking at the nullifiers, you can't work backwards to figure out which UTXOs are being spent. So this way, we can even hide which UTXOs are being consumed by a transaction. For the output UTXO, they just get constructed to be new UTXO hashes, and they must obey the mass conservation rule, meaning the sum of the input UTXO values versus the sum of the output UTXO values, they must equal. And finally, zero knowledge proof is a critical part of this because, as you can see, the transactions are just a bunch of hashes, right? So how does the smart contract know that these input hashes and output hashes represent a honest transaction? So that's what the zero knowledge proof is trying to do. And each proof, depending on exactly what our privacy requirements are, will have different statements in them. And we'll see the details in the following slides. So I've mentioned a couple times these patterns. So you can definitely build a privacy token by just having mass conservation guarantees. So maybe your system doesn't need anonymity. So your zero knowledge proof can simply prove that the input UTXOs and output UTXOs, those hashes represent a transaction where the sum of the input equals the sum of the output. So nobody is trying to cheat by giving themselves more than what they have. And then if you think about this, the sender will have some new UTXOs promised to the receiver, and those hashes represent some value. How does the receiver know what value those hashes represent? the sender can either send the receiver those secret values in the off-chain channel, which would be the case with the first pattern, or we can encrypt those secret values as part of the transaction and send those encrypted values along with the transaction so that the receiver is guaranteed to have the value as part of the transaction so that they can decode and decrypt from the transaction payload and get the value corresponding to the UTXO they now receive. So now if we add anonymity as a requirement, then we have a even more complex circuit that has both the mass conservation rule, an on-chain data availability rule, plus we're hiding the ownership information of each UTXO. So the circuit will get more and more complex, and we'll see how they're constructed in particular very soon. So as the circuit complexity gets bigger and bigger, the circuit size will be larger and larger, and the proving time accordingly will take longer and longer. So that's sort of the balance you have to think about. And this is the critical part of this UTXO toolkit concept. It's not a sort of one solution fits all kind of approach. It's approach where you have all these choices, and depending on your specific use case, you can make a optimal decision between the speed versus the complexity of the requirements. And by the way, because at the moment, the implementation are built on Snark, regardless of how complex the circuit is, the proof size is always constant. And as a result, your validation verification time is almost constant. I say almost because it still varies a little bit depending on your input size. But the overall time doesn't, overall verification time doesn't vary that much based on the circuit complexity. Okay, so maybe we should pause here and see if we have any questions. Kevin, do we have any questions from the audience?
Nothing yet that I've seen come across.
Okay, sounds good. Okay, so let's look at what using commitments rather than values look like. So what you're seeing here is what Bitcoin looks like, which is every UTXO has the value of that state and then the ownership of that state. It's not, this is a simplified picture. Rather than just simply specifying the owner, it's actually specifying the spending condition. And the most popular spending condition in Bitcoin is obviously proving that you have the private key of the public key that's logging the spending of that UTXO. But there could be other more complex conditions that can be specified. But just to make it simple to follow, we can conceptualize that each UTXO just has the value and the owner. You can spend it if you can prove that you are the owner of the UTXO. So in this picture, we have 3 UTXOs across 2 owners. Alice has 0.1, Bob has 15.8 across 2 different UTXOs. So now if we want to build privacy, then we just want to hide it. And a very useful way to hide the value is to use hashes. So now we're going to use the value, the ownership public key, plus a salt, a unique salt for each UTXO, and then take a hash of it. And this will be our UTXO on-chain instead of the clear values. So now with this, we have accomplished hiding the value on-chain, so that when even if someone contributes a node into the Ethereum network, they can download the full ledger, but then when they look at the on-chain state, all they see is a bunch of hashes. It's worth mentioning that in terms of hashes, the most well-known hashes has been SHA-256 and SHA-3 with K-check. That's not what we're talking about here. We're using a different class of hashes that are used inside zero-knowledge proofs. We don't have time to go through the specific reasons for that, but just understand that the SHA-256 and all the well-known hashing algorithms are very expensive to prove inside zero-knowledge proof circuits. So new hash algorithms are being designed to make them be much more efficient inside zero-knowledge proof. So Poseidon, MIMC, those are designed for this purpose. Okay, so let's look at the first privacy pattern. In this picture, if you focus on the blockchain state first, we have this hash sign representing that these are hash-based values on the chain. So transaction 1 is spending UTXO 1, 2, and 3, and generates 2 more new UTXOs, 4 and 5. Those are just hashes. And corresponding to these hashes, the private states belong to the owner of them. So they're private because only the owner of those private states know what they are. So party A owns 1 through 5, party B 5 through 7, and party C knows 7. So some of them are shared between the two because 5, as you can see here, was proposed by party A, and it's given to party B. So party A knows the value of 5, but party A cannot spend it because B is the designated owner of this UTXO. So in this case, what we do here is we use a transaction and we construct the transaction with 3 UTXOs in the input and 2 UTXOs 4 and 5 in the output. And then we generate a proof with our zero-knowledge prover saying that these really belong to the sender, party A. So party A has the private key that corresponds to the public key that's in the hash of these states. Again, this is the part of the pre-image of the UTXO hash. So the proof says party A has the private key for that public key. It also says that the sum of 1, 2, 3 equals to the sum of 4 and 5. So that's the mass conservation rule. So then within the smart contract, the Solidity code can look at transaction 1 and say, okay, I'm going to do a validation on the proof. If the validation is successful, then I'll let your transaction through. And when the transaction is committed, then the new UTXO will be announced as a event. So party B will index that UTXO, and okay, so at this point, party B sees there's some hashes that are marked as party B being the owner, but party B has no idea what's the pre-image of that hash. So that has to come from a private channel between party A and party B. So A has to send the secrets, which is the value and salt, in the secret channel to B directly. At that point, B has the necessary information and will be able to spend the new UTXO it received from A. Similar for transaction 2 between B and C. So let's look at exactly how this circuit is constructed. So when you look at a zero-knowledge proof circuit, the first thing you need to think about is what are the public inputs and what are the private inputs. In this case, we need to prove that party A has possession of the private key that corresponds to a public key that's part of the hash pre-image. So this is what the zero-knowledge proof circuit needs to do, is to use the private key as private input and then derive the public key. And then later on, we can use the public key to calculate the hash and then prove that this hash matches the input UTXO. So then the next step is the circuit will calculate the hash and then check that the calculated hash matches the hash in the input. So at this point, the proof has attested that A is really the owner of the input UTXOs to be spent. And finally, the circuit also needs to calculate the sum of the values of the input and sum of the values of the output. And both of these values are part of the private inputs, so they don't get disclosed by the verifier to the verifier. But at this point, the zero-knowledge proof circuit is done. So the proof can be generated so that all these statements can be verified to be true. Okay, so now let's look at some code to see how exactly that is constructed. This is a project that uses confidential UTXO with Circom. There are several parts to it. At the high level, we have the part that deals with the zero-knowledge proof aspect, how to design the circuit, and specifically, we're using the Circom toolkit. The ecosystem is very mature. There are a rich set of zero-knowledge proof circuit libraries, so you can do a lot of things from the library, so you don't have to construct everything from scratch. There are very good quality language SDKs for JavaScript. So you can do this in the browser or as part of your Node.js runtime. There's also C++ runtime, so you can have a faster proving time if you do the proving in the server.
We're still seeing the PowerPoint slide.
Ah, okay, sorry. I think I
that.
need to reshare. 1 second. Can you see it now?
There we go.
Okay, awesome. So so this is this project has the two parts. One is the zero-knowledge proof with the Circom circuits, and then test the code using JavaScript that makes use of the library I was referring to. These libraries. So then at the end of the day, you can have a JavaScript SDK plus the proving keys. So these are required for generating the proof at runtime. And finally, a second part of that is the verifiers in Solidity. So at the end of the day, we need to validate that a transaction that's submitted to my Solidity code has a valid proof, and that is verified here in Solidity code. So this whole class is generated by the Circom compiler. Well, actually, it's generated by the Snark.js runtime that's based on the output of the Circom compiler. So you just need to call the verify proof function from your main Solidity class, and then you can verify the transaction and decide accordingly. So let's look at the circuit a little bit more. At the high level, we have the first pattern, we just call it confidential UTXO1, which does the things we just described earlier. So sender's private key is going to be a private input. And as you can see here, input UTXO, output UTXO, those are public inputs. And the output owner's public key is also public input. So the idea of zero-knowledge proof is that it's going to do the calculation that that needs to be done, and then you have to publish your circuit so that the verifier can be convinced that you're speccing out your circuit to do the right calculation so that the proof it generates represents the right statement. So what we're doing here in the circuit is first, we're using the private key to derive the corresponding public key. And then we're using the public key inside our check hash and sum circuit, which I will open now, so that this public key was derived from the private key, and it's now used to calculate the hash. And then the calculated hashes are compared with the input UTXO commitments. So this comparison here proves that I have the correct private key, so that because I derived my public key from that, and then I use this derived public key to calculate the hash, and eventually that matches the hash in the public input. So now I have demonstrated that I'm the owner of this UTXO. So that's what this step accomplishes. And next, we also prove that after we have summed up all the inputs and outputs, they are equal. So this also proves that this is a mass conservation obeying transaction. So if any of these rules are broken, then the proof cannot be generated successfully. So, okay. That's the first circuit. We'll go a little faster later on because a lot of information is common. So you may see a potential issue depending on your use case. A potential issue can be, what if the sender hold off sending the secrets to the receiver? The receiver, even though has received the transaction output, so that there is a output UTXO with themselves marked as the owner, without knowing the secrets, they won't be able to spend it. So that's a potential attack vector in certain use cases, but in other use cases, this may not be a problem. So if this were a problem, then we need to address this with the pattern number 2, which is everything we've done in circuit number 1 plus an additional step of encrypting the secret values, so that only the receiver can decrypt that value and no one else. And this is accomplished by doing a Diffie-Hellman-based key exchange to generate a shared secret between the sender and the receiver, and then use that secret to encrypt our values. So in this case, you can see no private channels are required between the parties, between the senders and receiver. And instead, the receiver can just take the encrypted values from the transaction and then decrypt from that to recover the secrets. So this is better in terms of the receiver is guaranteed to have the value available to them that they can decrypt to recover the secrets, and then they will be able to spend their UTXO. So our circuit will be a bit more complex now. So we still have the same private input with the private key from the sender and the public key from the receiver. But now we derive using Diffie-Hellman. It's a understood protocol to generate a shared secret without the two parties sharing anything other than the public information. So this shared secret then is used to generate a ciphertext, and this ciphertext is a public output. This will be included in the transaction. And it's important to generate the encrypted value from the circuit because we want to prove to the receiver that this bunch of gibberish, right? Because when you look at a ciphertext, it's, nobody can make sense of it. Certainly the smart contract wouldn't know what this ciphertext was generated from. We need to convince the smart contract that this bunch of gibberish was actually a decrypted value that's guaranteed to be decipherable by the receiver. So that's a critical part because you can send a bunch of gibberish, right, to the smart contract, and nobody knows if it can actually be decipherable by the receiver. But having done this by the zero knowledge proof circuit, we have proven that the ciphertext is properly generated according to our shared secret between the sender and the receiver. So then what the receiver can do is after having indexed the transaction and listened to the events, take the ciphertext out of the event, and then using Diffie-Hellman again, the receiver can use its own private key plus the sender's public key and recover the same shared secret that was used to encrypt and now use it to decrypt and then recover the value in salt. So the code that's involved there is two parts. First, we do the Diffie-Hellman key exchange. So this is pretty well understood in cryptography using a private key. This is from the sender and the public key from the receiver. We will derive a shared key and then the shared key can be fed into a encryption scheme that will in fact will be based on a Poseidon hash to encrypt a value here, because in the token based use case, the plain text here is just a big number. It's just a number. So it's very friendly to do with a Poseidon type of hash. And this is the top level circuit for the second pattern. You can see it's got the majority of the same input and output, but there's additional output for the ciphertext. We don't need to go to the details there. So let's look at the third pattern. This gets a bit more complex by introducing anonymity. So what we need to do in terms of anonymity is we need to hide the ownership information of each UTXO so that when you look at a transaction, you see some party is sending some value to another party, but you don't know who is sending something to who. In addition to that, we also want to hide which UTXOs are being consumed because as part of the anonymity requirement, we want to hide, we want to prevent anyone to be able to sort of build a spending graph leading from the consumed UTXO to the output UTXO, which then will be further consumed to lead to new UTXOs. If you are able to build a graph like that, which will be the case if you have ownership information and if you disclose the input UTXOs, then there will be leakage to the ownership information at some point. So we want to hide that. And to do that, we introduce this concept of nullifiers. What it is it's a secure hash that is securely bound to the UTXO hash. So it's one-to-one binding between the two. And given a UTXO, it's impossible to guess what the nullifier hash should be unless you have the secret information, and vice versa. Given a nullifier, you have no idea which UTXO it's bound to. So the specific design for the nullifier is we replace the public key from the pre-image with the private key. So between the two, we have accomplished the requirement for the nullifier. Only the sender will have the private key, so no one else can generate the nullifier. And because of the one-to-one binding between the public key and the private key, we have achieved the one-to-one binding between the UTXO and nullifier. So this is what the flow looks like for this use case. Now we can see that all these states are lined up in the collection, and no one knows anymore for a particular transaction which of these UTXOs are being spent because of the usage of the nullifiers here. And the binding is illustrated with these dotted lines, and that's only known to the sender. No one else knows the binding here. So how do we prevent double spending here? That is done by just keeping track of which nullifiers have been used before. So the smart contract will keep track of all the nullifiers that's been used in previous transactions. So if someone attempts to spend or double spend a UTXO that's already been consumed, they would have to use the same nullifier corresponding to that UTXO, and as such be called by the smart contract because it will have seen that nullifier before. So the circuit here does everything in one or two, plus checking the nullifiers is properly constructed. It also needs to, because we're hiding which UTXOs we're spending, we have to check that the nullifiers are consuming some UTXOs that are pre-existing. It's not consuming some UTXOs, that hasn't been constructed before. We could just check that the input UTXOs belong to a map, but that's very difficult to do within a zero-knowledge proof. Instead, we use a Merkle tree proof to show that the UTXOs in the input belong to a tree that's represented by a Merkle tree root that's maintained by the smart contract. So the smart contract keeps track of the input UTXOs and then use a Merkle tree to always calculate the hash. So when the proof shows that there are input UTXOs that belong to a tree represented by that tree root hash, then the smart contract can be convinced that they really belong to the input UTXO tree. So some details of how this pattern is implemented is we add the check of the nullifier, which involves using the owner's private key and then calculate that they correspond to the nullifiers in the input list. We also do the smart contract. This is the Merkle tree proof part that uses a Merkle proof generated by the sender and then compare that against a Merkle tree root, which is a public input. Let's see if we, okay, so do we have any questions or do we have a couple minutes to go through a quick code run?
There's only one quick question, Jim, and that was if you would be able to share some of the GitHub repositories you're working from there.
Okay, so at the moment, this belongs to a private repository, but we're working on making that public. So stay tuned.
Perfect.
Okay, so we may have a few minutes. Okay, I'm gonna show two things. For the zero knowledge proof, we have, I mentioned that we have tests that shows the zero knowledge proof is working properly. For example, we can, construct some input UTXO, output UTXO, and then do a witness generation, and then check that the witness are properly constructed, and then generate the proof, and then verify the proof can be verified against the public signals. So all that can be tested out, and we can quickly do a demo here. Mainly want to show you that the proving time with this is a completely JavaScript-based implementation with WASM as the circuit runtime. The proving time is about 1/3 of a second. If we used a binary C++-based prover, then this time will be even faster. Similar for number 2 pattern. It gets a bit longer to generate because the circuit is more complex. 3 is going to be even longer because it's a much more complex circuit. But these numbers are still tolerable, considering these are JavaScript-based calculations. And certainly using a binary prover will improve the time as well. So this is just on the circuit itself. So eventually we want to do the full end-to-end by generating the proof and then submit the transaction to the smart contract so that the proof can be verified on the smart contract on Ethereum. So we'll do that here. So we have hard hat-based tests with our UTXO implementation that utilizes the verifier from the generated solidity like this. So we can do the test. So this is our solidity implementation for the first pattern. And what we are doing in the in the contract test code is we're constructing some UTXOs between Alice and Bob and doing some transfers between them with both successful and failure scenarios. So once we publish the repository, you will see the details of how to do that. And you can see this is now successfully constructed and verified with the smart contract on EVM. So I think that's all the time we have for today. I can run a bit more for 2 and 3, but they will all look about the same. So maybe we open up to see if there are any questions from the audience.
Awesome. Yeah. And if folks want to drop questions into the chat, we can take them from there. Or if you want to raise your hand and ask, I can unmute you. Yeah, thanks, Jim. We'll get those sent out after. And sorry, that was directed to Jim Mason.
Okay, so in real world implementation, does the ZKP go to blockchain or is it running from backend server? Okay, so in real world implementations, you can do either depending on the use case. If you're running a token economy with finality guaranteed by on-chain verification, then you want to validate the zero-knowledge proof in smart contracts so that each transaction can be finalized right away because you know that transaction is valid through validating the zero-knowledge proof. Or you can build a quote-unquote optimistic system where the smart contract assumes the ZKP is correct. And because the ZKP is recorded on chain, they can be later validated by some off-chain components. And then if they fail at that point, you can do a challenge to say, I caught someone cheating, and then there are some consequences. So just like how optimistic block layer 2s are built, you can implement a optimistic system like this where verification of the zero-knowledge proof is done off-chain instead of on-chain. That's a great question. I think we're right on time.
Yeah, it's like a good place to wrap it. So thanks so much, Jim. It was a great session. I know I learned a lot, so appreciate you putting that together and taking us through it. For everybody else, if you have any questions or have a project you're working on where this would come into play, please don't hesitate to get in touch. I dropped a number of links into the webinar chat there where you can get in touch on the website or follow us on socials. We also always post links to these events on our social media channels. So, follow there to stay in the loop on what's next. But thanks again for joining. Thanks again, Jim, for presenting. And with that, we'll call it a wrap.
Thanks, everyone.